Next up is our beginning of the medical physics topic, and we're going to start with X-rays. This is going to be quite a long video, there's quite a few slides, so bear with me, there's a lot of information you need to absorb. So we're going to look at X-rays, how they're produced, how they interact with matter, how we can take better X-ray pictures in medicine, and then we're going to have a quick look at CAT scanners as well. So, get your writing hand ready. So, what are X-rays? Just a brief recap. They are electromagnetic waves. They are lower energy and frequency than gamma waves, and they have a wavelength of 10 nanometers to 0.01 nanometers. And obviously we know that they have very similar properties to light because they are electromagnetic waves, which means that they will do wave-particle duality. They do have wave-particle duality. So, how do we produce X-rays? Basically, we take a high energy electron and smack it into a piece of metal. The electron's kinetic energy then gets transformed into electromagnetic energy, and it generates two different types of X-rays. The first are called Bremsstrahlung radiation, or braking radiation, or white X-rays, and the second type are called characteristic X-rays. Now I'm going to tell you a little bit about these two types. The specification doesn't explicitly say that you need to know the difference, but I think it will be helpful for your understanding of exactly what's going on if you can describe how these are formed, because it will really help reinforce a lot of the ideas we've been studying so far and remind you of some of the stuff from AS as well. So, Bremsstrahlung radiation is basically the energy that is released from the electrons being slowed down. So the energy that they lose on hitting the metal target is then just released as electromagnetic energy. Basically this is because when you accelerate a charge, it emits electromagnetic radiation. It's sometimes called synchrotron radiation. And if the energy that I give the electrons is high enough to begin with, the energy that is given out is in the X-ray region. You can tell the Bremsstrahlung radiation because it's a continuous spectrum of radiation, and as it becomes more intense, it shifts towards the higher frequency as you increase the energy as well. Okay, so you can see that the wavelength decreases as I increase the kinetic energy that I give the electron to begin with. So this is 20 kilovolts, 30 kilovolts, 40 kilovolts, 50 kilovolts. That would be the voltage that is accelerating the electrons. Okay. Now, the reason that Bremsstrahlung radiation is continuous is because the electron that I'm putting in can lose any amount of its kinetic energy. It could lose all of it, it could lose a little bit of it, it could lose half of it. So that gives me a range of values for the frequency or the wavelength of the X-rays that are given out. So for instance, if I have an electron with a kinetic energy of 70 keV, it could lose all of that, none of it, or anything in between through the Bremsstrahlung process. So that means that the X-ray could have anywhere between 0 and 70 keV. Here, 70 keV is the energy that would correspond to the cut-off wavelength. So if you recall, we looked at the energy of photons and then being calculated by E equals HF or E equals HC over lambda. So if I know what the maximum energy that my photon could have, if I know what that maximum energy is, I can use that to calculate what the smallest wavelength or the highest frequency that photon could have. So I could check that it really would be an X-ray photon. So that's Bremsstrahlung. Second type are characteristic X-rays. And characteristic X-rays are produced by transitions of orbitals from outer to inner shells. So this is similar to what we were talking about with the spectra and emitting different types of light. Well, in fact, it's not similar, it's the same thing. So when the electron hits, what it can do is it can excite electrons from inner energy levels up to higher ones. Then the higher energy level electrons then fall back down to where they were before, and if that energy gap is sufficient or correct, I can get out X-rays. Now, these are called characteristic because they are based on the binding energy for every element, so based on the energy levels. And the characteristic X-ray will be specific to the element that I use in my metal target, because the energy levels are specific to those metal targets, which is why it's called characteristic. Whereas with bremsstrahlung, we've got the range of X-ray energies. With characteristic, they're very fixed, very discrete. We just get these big peaks of energy that we get out. As a general rule, the characteristic X-ray energy increases as you increase the atomic number of the element. So this allows me to choose how much energy my X-rays have, which can be useful because sometimes I want high energy X-rays, sometimes I want low energy X-rays. It depends on what part of the body and what it is that I'm looking for. So if we do the graph here, you can see here that we've got two sharp peaks. So I've got an alpha peak and a beta peak, and these are from our molybdenum targets. This was from flying X-rays at molybdenum. Down at the bottom, I've still got this continuous range because I've still got the bremsstrahlung radiation. So the continuous section of the X-rays that are produced are the bremsstrahlung. I then get these specific peaks at specific wavelengths, and that is the characteristic ones. And these are K alpha and K beta because it's telling me which electron shell the transition is happening from. Okay, so as I said, you can still see the bremsstrahlung bit on the bottom. So what's happening inside the tube? Well, basically, this is what an X-ray tube looks like on the inside. I've got, in essence, just a kind of like the element inside a filament bulb, only it's a bit stronger. And all I do is heat it up. I get it really, really, really hot, and that causes electrons to be released from the metal. That's called thermionic emission. I then apply a really high voltage. So this pink bit here is just showing you that I've got a potential difference across here. And that potential difference is going to accelerate those electrons. So we just use the electric field to cause those electrons to start moving and give them the energy by making them pass through the potential difference. They then go flying up till they hit the metal target. Now the silver bit, the grey bit here, that is the metal target. And it's normally at an angle so that the gamma rays that come off where I want them to do, and the X-rays will come off down here. Now the metal target is embedded in a large piece of copper, and that piece of copper will often be able to rotate as well, and that is in order to disperse the heat because it's going to get very, very hot. But obviously I don't want my metal melting. That would be, expensive, unpleasant and dangerous. So we take a lot of measures to make sure that we can deal with the amount of heat that we're producing here. So talking about this target material, when I pick my metal, it needs to have a high proton number because I need to have energy transitions that are going to produce X-rays. It needs to have a high melting point because it's going to get really hot as well. Generally we end up with tungsten. Tungsten is the most common metal that's used. If I need softer X-rays, so if I'm looking at low energy X-rays, we're looking at soft tissue, we often use molybdenum. So those are two examples that you can give for target metals. So that is how we produce our X-rays. Next thing we need to know is how do they interact with matter. So there are 4 ways that you need to know about that X-rays interact with matter. They are simple scatter, photoelectric absorption, Compton scattering, and pair production. Now, this is a little bit new in the new specification because they've separated simple scatter and Compton scattering. So I wouldn't be surprised if something came up on that, or they specifically asked about one of those two. So I'll tell you a little bit more about each of these. So we've got simple scatter. Simple scatter is most important for the very low energy electrons. I did that on purpose, honest. The thing you all are going to do in the exam is you're going to mix up the word electrons and photons like I just did. So don't. Learn from my mistake and just don't do it. So I'm going to start it all again and I'm going to get it right this time. So simple scatter is most important for the X-ray photons that are at very low energy. When these photons hit orbital electrons, they don't have enough energy to remove the electron. They don't have enough energy to do anything to the electron, really. They just collide with it and bounce off. So its direction is changed, but its energy isn't. So simple scatter is just where a very low energy X-ray photon hits an orbital electron and its direction is changed. Its energy, however, is not. Now, because X-ray machines tend to use potential differences of more than 20 kilovolts, this mechanism is not going to be happening with hospital X-rays. So next up, we've got photoelectric interactions. So this is where I get photoelectric absorption. This is where a higher energy photon is absorbed by an orbital electron, and that electron is then emitted. It escapes the atom. So the incoming X-ray photon gives the orbital electron sufficient energy that it is able to escape. This is the most dominant mechanism for lower energy X-rays on the scale, so higher than for simple scatter, but comparatively low, so we're talking less than 100 keV. Next up, we've got Compton scattering. So Compton scattering is where my incoming X-ray photon has got quite a lot of energy, and this one interacts with the atom. It gives the electron in the atom enough energy to be emitted, so the electron leaves, but the X-ray photon still has some energy left over. So the X-ray photon continues on its way, it's just scattered at a different angle. So with Compton scattering, higher energy X-ray photon hits an orbital electron, the electron is emitted, and the X-ray is scattered with lower energy. So this is significant for the range of about 0.5 to 5 MeV photons. And our final attenuation mechanism is something called pair production. And this happens with the highest energy X-rays. And this is when the X-ray photon comes near the nucleus and it spontaneously becomes an electron-positron pair. So pair production, it produces a pair. And the minimum energy for this interaction is 1.02 MeV. I'm going to ask you why in class. Why is there a minimum energy for this one? Okay, so those are our 4 attenuation methods, our 4 methods that X-rays can interact with matter. I just wanted to very quickly review intensity with you. This is an AS thing, but I'm just going to go over it anyway. So intensity is the power that's transferred per unit area. So intensity equals power over area. Its unit is watts per meter squared. There will be questions about intensity, I would imagine, when it comes to X-ray beams, when they're asking you about how much or what's the intensity of a beam that's hitting a surface of this many millimeters and things like that. Okay, now I've used the word attenuation a couple of times, and that is because attenuation is the name of the process where X-ray beams lose intensity. There's mechanisms we were talking about, so the not simple scatter because it doesn't lose any energy, but Compton scattering, photoelectric absorption and pair production, those are attenuation methods, because in all 3 of those the X-ray photons lose energy when they interact with matter. And there is a way that we can calculate and we can look at how much energy they are losing and what's causing this. So attenuation is exponential, so yet another one that's exponential. So this time we've got I equals I naught e to the minus mu x. So I naught is the initial intensity, I is the intensity of the beam when it comes out the other side, x is the thickness of the material it passes through, and mu is something called the linear attenuation coefficient. So linear attenuation coefficient is just a measure of how strongly the material attenuates, how strongly it absorbs the energy of the X-rays. So if I've got an exponential relationship, that means I'm going to have another one of these half values again. So kind of like we've got half-life with radioactivity, and we had your time constant in capacitors. We've got another one for attenuation as well. So let's just think about what we might want to graph when we do these. The thing that's likely going to change, or the only things that could change, is the intensity that's coming out and the thickness of the material it passes through. So if I plot that graph, it should look exponential. So I get this exponential curve as it goes through the graph, and if we look, here is my half-life, except here it's a half thickness, because it's thickness along the bottom. So for equal increases in thickness, I halve the intensity that's coming through. Okay, so half thickness, similar to half-life, thickness of the material that ray passes through in order to halve it. And it's going to depend on the density of the material, so basically the linear attenuation coefficient. Okay, so next thing we need to talk about is how we can make X-rays better, how we can improve the contrast. And in order to improve the contrast, we use something called contrast media. These are materials that have high Z numbers, which means that they can absorb large amounts of X-rays. And that allows us to sort of coat soft tissue with an X-ray absorbing material so that we can see more detail about it with the X-rays. So they have high Z numbers, which means they absorb X-rays. Another way of saying that is that we use radio-opaque materials. So the examples that you need to know are iodine, which can be injected into the bloodstream, and we use it to look at the outlines of blood vessels in the heart with X-rays. The second is barium, which we often swallow as barium sulfate, and that allows us to look at the outline of the stomach and the intestines. So the idea here is it gives us better contrast, it lets us see the outline of soft tissue by coating those materials with radio-opaque substances. Okay, so that's how we can make X-rays better, but X-rays are pretty limited, and basically the limitation of X-rays is that we are getting out 2D pictures of 3D objects. So we can end up with bits of bone and organs being overlaid over the top of each other, so we can't see properly what's behind things. So what would be better is to have a 3D picture. And this is where CAT scans come in. Now CAT stands for Computed Axial Tomography. And this is the process of using a computer to generate a 3D image from a series of 2D X-rays. So this is a CAT scanner here. This is what it looks like. And the way it works is that there is an X-ray machine basically inside this bit here and a detector on the other side, and they can rotate around the patient. So the machine rotates around, it produces a thin fan-shaped beam which takes images through slices of the patient. After it's gone all the way around, it moves down the patient to take more slices. Or in some cases it can just spiral along, so with every picture it takes, it moves along the patient ever so slightly, so it spirals along the axis. And the signals from the detector are then sent to a computer which processes the information in order to form a 3D image. So that's a CAT scanner. Describing how this works could be a 6-mark question. Things they would be looking for is the thin fan-shaped beam, slices of the patient, that the X-ray machine is rotating around the patient, that it spirals along or moves along the patient's body. The signals are sent to a computer, and the computer forms a 3D image. Those are where the marks are going to be for this. Now, just a little quick comment, just because I have a pet peeve. This is a CAT scanner, capital C, capital A, capital T. This is a CAT scan if you don't capitalize. The difference between it being an acronym and a word. So just don't do that one. Okay? Little easy mistake to avoid. Right, so that is it on X-rays. So remember, any questions? Ask when you see me.